Hi, I apologize for the poor quality of this video, but I'm currently traveling for work, so I'm doing this on my cell phone. My laptop was being uncooperative, and I wanted to make sure I handed this in on time. So, for our final exam review, we'll be doing 10th edition textbook, chapter 11.5, question 76, where it's asking us to find both the angle of intersection between two planes and the line of intersection between two planes. So we're going to go right to it. As you can see, we have the planes equations on the paper. What we're going to first need to do is turn them both into a general form of a plane equation. And to do that, we need to make sure both of them equal 0. So as you can see, I've gone ahead and set both equations equal to 0. The next thing is we're going to need to find the normal vector for both these planes. As we remember from 11.5, just taking the coefficients from the general form equation of a plane will give us the normal vector for the plane. So as you can see, I've gone ahead and got the normal vectors. I labeled one n sub 1 and the other n sub 2. Now to find the angle of intersection, the equation is cosine of theta equals the absolute value of the dot product of the two normal vectors divided by the magnitude of both vectors. Now remember, we use the absolute value because we want to force this to be an acute angle. So as you can see, we've done the dot product of the two vectors. That gives us a -4. And as you can see, we've gone ahead and calculated the magnitude of both vectors, square root of 46 and square root of 27. So plugging those into the equation, we get the absolute value of -4 divided by the square root of 46 times the square root of 27. So we clean that up a little bit, and we eventually get to the part of cosine of theta equals 4 divided by 3 times radical 138. We need to get theta, so we're going to get it by itself, and we get theta equals the arc cosine of 4 divided by 3 radical 138, which approximately equals 1.46 radians, or 83.5 degrees. Now, the second half is to find the equation of the line of intersection between two planes. And I've gone ahead and broken this down step by step because this is how I like to handle these kind of problems. So as a reminder, to find the equation of a line, you need a point and a direction vector. So the first thing we need to do is find a point on both planes. To do that, we need to eliminate a variable. We want to look for opposite signs of the variable between the two equations. So y automatically had a negative in the first and a positive in the second. So I multiplied the second by 3 so we could cancel out the y's completely. And we ended up with 3x plus 16z minus 20 equals 0. Our next step is we want to solve for one variable. So as you can see, I go through the steps here of getting x isolated by itself. So we know x now equals 20 minus 16z divided by 3. Once we do that, our next step is we want to choose any value for the variable on the right side of the equation, then solve for the second variable. So in this case, I let z equal 2, substitute it in, and I found out that x equals -4. So now I have two values. I have the x value and the z value. To get the y value, we simply substitute back into one of the original equations to find the third variable. So I have written one of the original equations. I substitute in my x and my z value and solve for y, and I have y equals -9. Now I have the point. I do want to double check to make sure it works in both equations to make sure I did not make any errors with my arithmetic. So I have my calculated point of -4, -9, 2. I plugged it into the first equation, and it does equal 0. I plug it into the second equation, and it does equal 0. Great. We have 1/2 down. Now that we have the point, we need the directional vector. To get that, what we're going to do is take the cross product of the normal vectors for both planes. This will give a vector orthogonal to both original vectors. The orthogonal vector will be in the direction of the line of intersection. So again, we have our vector n sub 1 and n sub 2. And to get the orthogonal, we're calling that the v vector, we do the cross product. So as you can see, I set up our ijk, and I go through the cross product, and we get as our orthogonal vector -16i minus 31j plus 3k. So we now know that's the direction vector of the line of intersection. Now that we've done that, we take the point and the directional vector, and we find the parametric equations. As a reminder, For the parametric equations, x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct. So we have our point, we have our vector, we plug those in, and we have a set of parametric equations. X equals negative 4 minus 16t, y equals negative 9 minus 31t, and z equals 2 plus 3t. Now we could end there, but we want to ensure that the equations we have work. So the final step is to check the answer. We want to come up with another point on the line of intersection and repeat that step 5. Plug into the original equations and verify they work. So we're going to go ahead and let t equal 1. Plugging them into our parametric equations, we get x equals negative 20, y equals negative 40, and z equals 5. Again, we take the original equations, plug in our x, y, z values, and once again we can see everything works out. So this is how you can figure out the equation of the line and angle of intersection between two planes. Thank you very much.